Hello and welcome to today's episode of Beyond the README, where we'll be discussing transaction isolation in database systems. Transaction isolation has always been a topic of interest for me, as there are extremely subtle ways in which transactions in a database-driven system can impact each other. If you've developed any kind of database-connected application, you're likely familiar with the concept of transactions. Transactions provide the isolation in an ACID-compliant database, attempting to ensure that multiple readers and writers of a system do not step on each other's data. But did you know that databases provide different levels of isolation to prevent specific types of database phenomena? It's extremely important to understand these isolation levels so that you can choose the right isolation level for your particular workload. The isolation level needed for one workload may not be appropriate for a different workload. Additionally, you need to understand if the default level of isolation provided for your database system is appropriate for the workload you intend to run against it. So first, let me quickly describe the environment I'm going to use in case you'd like to follow along on your own. I'm using MariaDB deployed in a Docker container, along with a very simple banking database with a single accounts table. The table has 3 rows to represent different accounts. Obviously, this isn't a realistic database. However, it will allow us to focus on the topic at hand, and the concepts are portable to databases of arbitrary complexity. So you can apply these same concepts to your workloads. First, let's take a look at some of the different read phenomena that we might encounter in a database. The SQL standard defines 3 phenomena that we can experience. There are other types of phenomena that you might encounter. The 3 defined by the standard are dirty reads, non-repeatable reads, and phantom reads, and we're going to take a look at each of those. Database isolation levels are designed to prevent one or more of these phenomena at the expense of locking or other concurrency management mechanisms. The selection of a particular isolation level represents a trade-off. Performance is usually substituted for safety or data isolation. Different workloads are able to make different decisions about that trade-off. We're going to look at each read phenomena in turn. The Wikipedia description of these phenomena is pretty good for our purposes, but I would also strongly recommend Chapter 7 of Designing Data-Intensive Applications by Martin Kleppmann. It's an excellent chapter that can really take you through some of the edge cases you might encounter when using transactions in a database. So first, let's start by taking a look at dirty reads, and we're going to work through these examples at the terminal. So first, let's just read the basic Wikipedia definition of a dirty read. A dirty read, also known as an uncommitted dependency, occurs when a transaction retrieves a row that has been updated by another transaction that is not yet committed. So let's take a look at this in the context of our banking application. So imagine the following scenario. My wife and I are both out shopping separately. I'm thinking about buying some concert tickets, but I don't want to do that if I have less than $1,000 in my account. My wife is also out making a purchase for some things that we need at home. On the left side of the screen is my transaction, and on the right side of the screen is my wife's transaction. For the sake of demonstration, I'm going to lower the isolation level for both transactions to read uncommitted. Then I'm going to start the transaction. So first, I'm going to check my bank account to ensure that I have $1,000. I can see that I have at least $1,000 in account 1, the account I'm interested in. While I'm doing this, my wife over on the right also begins her purchase. Now I happen to check my bank account again, and I notice that suddenly we have less than $1,000. So I decide not to purchase the concert tickets, and I cancel my transaction. My wife also realizes in the middle of her transaction that we already have the necessities she was about to purchase, so she also chooses to cancel her transaction. Now, if we check our account again, we'll see that we still have $1,000, and I could have made my purchase. In this case, the data in my transaction is dirtied by the data in her uncommitted transaction. This is a dirty read and is almost always undesirable. One of the main purposes of a transaction is to only apply database changes when we commit the transaction. A dirty read violates this constraint. In this case, I specifically lowered the isolation level to read uncommitted so that we could observe this phenomena. Generally, the default isolation level in a database should be sufficient for preventing this phenomena. Next, let's take a look at non-repeatable reads, our next type of phenomena. So again, I do like the Wikipedia descriptions because they're simple and succinct. In this case, Wikipedia defines a non-repeatable read as occurring when a transaction retrieves a row twice and that row is updated by another transaction that is committed in between. So let's take a look at this in the context of our banking database. So I'm going to start by setting the isolation level to read committed. And once again, I'll show my transaction on the left and my wife's transaction on the right. So first, I'll start my transaction and grab my account balances. And I can see that I have $1,000. Now my wife is beginning her transaction as well. Once again, my wife goes to make her purchase. Now this time, if I check my account balance while her transaction is going on, we can see that my account balance has not changed because her transaction has not yet been committed. If she were to roll it back, I would be none the wiser. However, let's say in this case, my wife commits the transaction because we really do need those things she was about to purchase. Now when she commits her transaction, if I check my balance again, you can see that it's changed inside of my transaction. This time, of course, this change only showed up after she committed her transaction. But now we have a different problem. In this case, my read is considered non-repeatable because the data has changed out from underneath my transaction. Decisions made based on the data may no longer be valid because the data has changed. So in this case, if I looked at my account balance, saw $1,000, and made the purchase, we would suddenly be in the red. We can resolve this with the repeatable read isolation level. So let me repeat the experiment below after adjusting the isolation level. So first I'll set my transaction isolation level to repeatable read, and I'm just going to repeat the same experiment I ran. Once again, my wife makes her update and she commits the transaction. Now if I run my select statement, I can see that I still have $1,000 in my account, even though my wife's transaction committed, and this is because I'm working on a snapshot of the data. The view that I have of this data that I've selected is consistent with the first select, so I could come back many hours later after many changes. As long as this transaction is still open, if I run this same select statement, I'm going to get the same results. Now you might be thinking, wouldn't I always want to have the latest, greatest data during a transaction? Well, it really depends on the workload. Consider a long-running analytics workload that needs to frequently reread certain data as part of its data processing activities. It might not make sense for an analytics workload to constantly have data changing out from underneath it, as the conclusions of the data analysis may not make any sense anymore. Rather, it might make more sense for that analytics workload to run against a point-in-time snapshot of the data. Repeatable reads enable this. So far, we've been looking at single rows of data. Our third read phenomena, phantom reads, deals with ranges of data. Again, let's take a look at our handy Wikipedia definition. A phantom read occurs when a transaction retrieves a set of rows twice and new rows are inserted into or removed from that set by another transaction that is committed in between. So let's take a look at this phenomena in the context of the banking example. For this example, I'm going to set my isolation level to read committed for both of my transactions. So now let's consider a slightly different scenario. I have $500 to deposit into my various bank accounts, and I want to spread it out among any accounts that have less than $750. So I fire up a transaction and check my account balances. I query my bank for any accounts with less than $750. Meanwhile, my wife is also beginning a transaction. She is going to simultaneously withdraw some money from account 1. She commits her transaction, and suddenly I have a new row that appeared in the middle of my transaction. Similar to the non-repeatable read use case, my decisions that I made based on the range of data I selected may no longer be valid. And in MariaDB, this is actually prevented using the repeatable read isolation level, which operates from a consistent snapshot of the data from the beginning of the transaction. So let's see that in action. So in this case, even though my wife committed her transaction, because I performed this first read, I'm now operating on a snapshot that contains this data I selected. So that row does not show up in my result set. So now we've taken a look at these different read phenomena, let's talk a little bit about isolation levels. Isolation levels allow you to control the trade-off that you make between performance and isolation. You've seen the first 3 levels of isolation at various points during the examples. We've seen read uncommitted, read committed, and repeatable read. But you haven't seen serializable yet, and we'll take a look at that in a moment. Serializable is the most strict level of isolation. Typically, these isolation levels can be changed on a global, session, or per transaction basis. And it's very important to understand that different databases may implement these slightly differently. So you should always test and understand your chosen database with your specific workload to ensure that it's going to prevent any phenomena that you want to avoid. It's not enough to test just with toy data. You should be testing your database and your isolation levels with the real data and the real transactions that you expect to see run against that data. So now let's talk about serializable isolation. Serializable isolation is the most strict form of isolation, and the result ensures that the result of 2 concurrent transactions is exactly the same as if they happened one after the other. This is also the least performant method of isolation, so it's not necessarily appropriate for all workloads. Let's take a look at serializable isolation in the context of our banking database. So I'm going to start by setting my isolation level back to repeatable read, which is the default level of isolation in MariaDB. Next, I'm going to kick off 2 transactions, one for me and one for my wife. I'm going to start by checking my account balance. I see that I have $1,000, so I'm comfortable making a $500 purchase. Meanwhile, before I've committed, my wife also takes a look at our account balance. She also sees that we have $1,000, so she's getting ready to make her own purchase. But just before she attempts this update, I commit my transaction. She then runs her transaction and commits it. Now we're suddenly in the red. So this is obviously undesirable and is not what we would expect if we ran one transaction after the other. In this case, we would have expected the transaction on my wife's side to end because it was making assumptions based on an old version of the data. So let's repeat this experiment at the serializable isolation level. I'm going to start by setting the isolation level to serializable for both sessions. And now I'm just going to repeat the experiment. I'll start my transaction, grab my account balance, and make an update. My wife also begins her transaction. And she goes to check her account balance. Notice how the terminal is hanging now. And this is because my transaction is blocking her transaction. So in this case, her read, which would normally be allowed at other isolation levels, is actually blocked because I'm currently updating that row. Now when I commit my transaction, her query is allowed to proceed. And she is now working on the most accurate copy of that data. Now she can see that we only have $500 in our account, so she rolls back her transaction. And you can see why you'd run into performance issues with this. Effectively, we have a writer blocking a reader in this case. Once I begin writing data to that particular row, nobody else can read it because we want to see what the result of my transaction will be so we can give those readers the most accurate version of the data. And so you can see why this might not be performant for certain workloads. In this video, you had the opportunity to look at different read phenomena in a database and see different levels of transaction isolation in action. Hopefully this gave you an idea of some of the considerations you should have when designing a robust database system. I'd really just like to leave you with a couple of closing thoughts. First, these kinds of issues can be very subtle, difficult to troubleshoot, and difficult to even discover. You really need to be testing your database systems to ensure that your workloads have the results you would expect. There can be different inconsistencies between different databases and different database engines, so really that testing bit is very, very important. More than anything, I hope I introduced you to something that you may not have known about. If you thought this was fascinating, I'd really encourage you to pick up a copy of Designing Data-Intensive Applications. It's how I got started on databases and how I really became interested in all of these subtle configuration parameters and considerations that go into data-driven applications. Thank you for joining me on this episode of Beyond the README. If you enjoyed this episode, be sure to share it with your colleagues, give it a like, subscribe to the channel. I'd really appreciate it, and I'll see you on the next video.